Hello everybody, Adam Lusek here, and today we're going to be talking about evaluating domain-specific retrieval-augmented generation chunking and embedding strategies. The general process of setting up a retrieval-augmented generation-based system usually starts with taking your documents, chunking them in some way, and then embedding them into a vector store. But one of the most common mistakes that I see is that most developers don't actually put a lot of thought into their specific chunking strategy, as well as the embedding model that they're actually using. But as we went over a few weeks ago in a video that'll pop up right here, right now, the actual chunking strategy that you use can greatly affect your efficiency, precision, and accuracy of the retrieval step of your RAG pipeline. And as we know, your generated responses from the language model are only going to be as good as the usefulness of the documents being retrieved. So last time what we did is we covered the various chunking strategies that the open source vector database team behind ChromaDB put out in their evaluating chunking strategies for retrieval report. And to summarize their general experiments and findings, they found that their novel cluster chunking algorithm with a chunk size of around 200 tokens tended to perform the best with precision with perfect recall, and the intersection over union metrics, which we'll break down in a bit here. And then their language model-based chunker achieved the highest recall. And while it might seem simple then to just go ahead and run with whatever the best performing chunker was from this general research, the key point here is that it is a general evaluation. And as we very explicitly know, if you're consistently working with or building these retrieval augmented generation or language model-based systems, a lot of these latest, greatest artificial intelligence technologies tend to operate very differently between your own domain-specific information and general evals. But thankfully, along with this wonderful research report from Chroma, they also open sourced their experimentation framework for being able to run the actual experiments across different chunking setups, across different embedding models, and determining all of these RAG performance metrics. So we'll be taking advantage of that today to show how to set up your own experiments so that you can apply multiple different kinds of chunking strategies, multiple different kinds of embedding models, and run literal evaluations to determine which combination of the two might work the best for you. As a plus, this framework allows you to also create custom chunking strategies, which we will be implementing, as well as take your own information and create the evaluation data set from it. So you don't necessarily have to use the general eval framework and the general data set that these researchers are creating these charts with, but you can actually use your own specific data to explicitly determine what chunking strategy and embedding model works best for your information. So as mentioned, we'll be re-implementing the evaluation framework that ChromaDB put out as part of this wonderful research report on evaluating chunking strategies for retrieval. I'll of course have this linked in the comments below. It's a phenomenal read, so give it a scan if you have some time. But along with this report, they put out the chunking evaluation repository here. In the last video, we went over all of the different text chunking algorithms that Chroma implemented and optimized, but today what we're going to be doing is actually looking at their evaluation framework for how they were able to produce and measure the results that they did. So to get started, you can either clone down the repo and path over to it, or you can actually use pip to install it like this so that you can just import it like any other Python package. This line that we have here in the first cell is going to do that installation, and then these are all the dependencies that this notebook is going to need. Now the first thing that we're actually going to go over, which isn't necessarily specifically related to the evaluation step yet, is actually setting up a custom chunking strategy. Most of the time, it's likely that you're going to use some form of pre-built chunker, but it's useful to know how to create your own if you need to really optimize for a specific data type or a specific format that you want to chunk down to embed into your vector database. And then of course, we'll show how you can actually literally measure the performance of your custom chunking strategy, as well as how it performs against existing chunking strategies. Very simply, the chunking evaluation repo includes a base chunker class, and the base chunker class expects to work with the evaluation framework a split text method that will take in some long string of text and return out a list of strings, or essentially our chunked document. So as a simple example, I'm going to create a sentence chunker here, and the sentence chunker is very simply going to take in the text, split it into all of its sentences, and then group the sentences into a specified number. So in this case, the default is going to be 3 sentences per chunk. So whatever text you spit in there, that will split it into chunks of 3 sentences. To demonstrate more explicitly how this works, what we're going to do is take a quick document that has a lot of text in it. So for our example, we're going to take the 96-page Form 10K from NVIDIA for FY24, which what I've done is converted it into just its text. So it's this nice long document of text. And then over here, what we're going to do is create our sentence chunker with 10 sentences per chunk, and then run our split text method across all of the text here. So once we do that, we see that we have about 175 chunks of 10 sentences. And then if we look at just a random sentence chunk, we can see that this has roughly, not going to count it all explicitly, but what looks to be about 10 specific sentences. So this is going to be the main chunking strategy that we're actually going to evaluate over the course of this notebook. But as I mentioned, it's not necessary that you create and evaluate a custom chunking strategy. You might just want to see already the existing implementations and evaluate those, and that is completely doable across this. I just wanted to put in a custom chunker so that y'all can know that it's there and the possibilities. So with our candidate chunking strategy to evaluate, what we need to do is actually talk a little bit about the metrics that we'll be evaluating against and the evaluation methodology here. The main idea that we're striving for here is a hypothetical perfect retrieval augmented generation retrieval system will only retrieve exactly what's necessary to actually answer a question. No more and no less. Chroma defines this a little bit more scientifically with this line here stating that for a given query related to a specific corpus or a given question related to a document, only a subset of the tokens within that corpus will be relevant. And then ideally, for both efficiency and accuracy, our retrieval system should retrieve exactly and only the relevant tokens for each query across our corpus. Optimizing this is of course going to be very reliant then on how we chunk the text in our document and our embedding model that we use for retrieval. And the intuition behind why our chunking and embedding strategy plays a part into this is because first, the embedding model is going to very directly affect how our similarity calculations for retrieval are ran between our queries and our chunks of text. And then our chunking strategy is going to very explicitly determine how the information is actually structured and presented. So it might include a lot of erroneous information that could misguide our generation step, or it could not include enough information and thus fail on our actual relevancy. Both the chunking and the embedding strategy are not necessarily independent of each other as well, so testing across multiple embedding and multiple chunking strategies to figure out what gives you the best accuracy, precision, and relevancy within your system is going to be crucial to test. So with that context, let's talk about what metrics we can explicitly use to actually measure that stuff. First, it helps to understand a little bit of the data set that we're actually going to be measuring against. So this is all going to take the form of queries and then references or highlights. Essentially the question and then the exact piece of text that's actually relevant to answering that question. This is going to have the start and end index in characters across the document so that we can see explicitly when this query is ran and what is retrieved by our system, how relevant that retrieved content is. As mentioned earlier before, a perfect performance from our retrieval, embedding, and chunking strategy would have that if we put in this query, it would only return this specific content, as this is all of the text that we would need to be able to accurately respond to that query. Essentially, how I've put it here is that a highlight or reference in this case is going to be a segment of text in the original document that contains the relevant information needed to answer our specific query. Highlights are going to serve as the ground truth against which we measure our chunking and retrieval performance. So through having a query and the exact relevant parts across a document of what information is needed to answer that query, we can actually dig into some specific metrics. The first of which is going to be recall. And recall is really going to measure what fraction of the important or relevant text is captured by the retrieved chunks. This is going to range from 0 to 1, where 1 means all relevant text was captured. A low recall then means our chunking strategy is missing or excluding important information. This is going to answer a question of how much of these important highlighted segments did we actually capture. So for example, if a highlight that we return is 100 tokens and our chunk is only capturing 70 tokens of it, our recall is going to be 0.7 or 70%. As a note, If you've worked with different information retrieval metrics, you might notice that we're doing a little bit of something different from our traditional setup. At this point, we're actually going to be doing token level instead of document level measurements here. This is going to allow us to be a little bit more specific towards RAG setups, as the document level retrieval doesn't necessarily matter as much as the internal content or tokens which are going to be processed across the pipeline. We'll then measure our precision, and precision here is going to be calculated by the length of overlap between our retrieved chunks and highlights divided by the total length of retrieved chunks. This is essentially going to measure how much of the retrieved text is actually relevant. Once again, this ranges from 0 to 1, where 1 means that all of the retrieved text was relevant. A low precision in this case might mean that the chunks contain a lot of irrelevant text. So it answers the question of how much of what we retrieved actually matches the highlights. So if we retrieve 200 tokens of text, but only 70 overlap with our highlights, we have a precision of roughly 35%. In looking at our chunking strategy in particular, it might be worthwhile not just looking at our literal precision, but also our theoretical max precision, which is where the precision omega comes into. Precision omega is going to measure precision in an ideal scenario where all relevant text is captured. This is going to show the theoretical best precision possible for a given chunking strategy. Like regular precision, but basically assumes you've retrieved all of the highlights. Lower precision omega means the chunks are inherently too large or poorly aligned with natural text boundaries. So this is going to answer the question of, if we made sure to get all of the highlights, how precise could we actually be with our chunking strategy? This is more so going to allow us to evaluate our chunking strategy independent of the actual retrieval step. Our fourth metric is then going to be intersection over union, which is otherwise known as the Jacquard index. This is calculated by the length of our overlap divided by the length of the union of retrieved chunks and highlights, which essentially is going to balance both precision and recall into a single metric. This is of course going to range once again from 0 to 1, where 1 is perfect overlap. So a low IOU here indicates either missing content, which is poor recall, or retrieving too much irrelevant text, which is poor precision. IOU in this case penalizes missing important content and including irrelevant content while handling redundant information. This metric is going to answer the question, how well do our retrieved chunks overlap with these highlights overall? So if we retrieve 200 tokens and the highlight is 100 tokens and the overlap is 70 tokens, we'll have an IOU of about 0.304. And so each of these metrics can tell us something on their own, but they work quite well together. A few examples of what you might want to look out for is that if you're seeing something like high recall but low precision, you're retrieving too much text and your chunking strategy might be too broad. But if you have low recall and high precision, you might be missing important content, or somehow your chunking and embedding strategy is either not retrieving or leaving out important content. A high IOU in this case is going to tell us an overall good balance of both. And then, as mentioned, our precision omega helps evaluate the chunking strategies independent of these retrieval steps. Another good final way of thinking about the precision omega, as Chroma puts it, is that it gives us an upper bound on token efficiency given perfect recall. So now that we understand what we want to evaluate, the metrics that we'll be looking at to run these evaluations, we now can look at how to actually do these evaluations. So Chroma has put together a default evaluation structure that includes 5 different text documents as well as the just shown respective questions and highlights data. So their text corpus includes a mix of both clean and unstructured text documents, hoping to try and simulate various text chunking and retrieval scenarios. These include these 5 documents. We have the United States State of the Union 2024, Wikitext, UltraChat 200K, a finance Q&A dataset, as well as a biomedical life and sciences journal dataset. These all include a specific token subset and a specific number of queries, which they nicely gave a good chart here showing exactly how much of each they're using. And along with that, they have 472 query and reference combinations, which will of course just have the questions as well as the specific text that is the ground truth only source needed to answer that, plus the start and end index across their total text document collection here. The general evaluation process is then going to follow this. So it'll take the text, chunk it using the chosen chunker, along with the chunk's start and end index, and then it will calculate first the retrieval performance. So it embeds the evaluation questions along with the chosen embedding function, then performs our vector similarity search to retrieve the top k most relevant chunks per question. And then from those chunks that we have using our chunking strategy, it will calculate our regular metrics of recall, precision, and intersection over union. And then for our precision omega metric, or precision with perfect recall, it will take a look at all of the chunks in the collection and then identify which chunks contain any part of the highlight segments, and then calculate our theoretical best precision possible if we were to actually retrieve all of the necessary chunks. So while the buildup to this might have seemed a little bit complicated, you can see now that it's very simply just going to run with our standard set of questions here, a simple vector similarity search, retrieve the top number of documents, and then they have the ground truth content here as well as where it's placed, and then it'll look at our chunking strategy, which is going to also show where our start and end index of the chunk is, and then compare the references to those chunks and other metrics here to both determine the chunking strategy's effectiveness and how the embedding model might affect these two. So I've gone ahead and instantiated our general evaluation from the repo here as evaluation, set up our sentence chunker with a sentence per chunk of 10, grabbed just our default embedding function that is going to be using text embedding 3 large so that we can compare it to the table above. And then all we need to do is run evaluation.run with our chunker and embedding function to get our results. Printing this out shows us a recall of 0.87, a precision of 0.037, a precision omega of 0.167, and an IOU of 0.037, as well as the standard deviation. These, of course, are going to be the mean across all of the documents. We can interpret this as such. Our 10-sentence chunking strategy demonstrated pretty strong recall performance of 87%, indicating pretty effective retrieval of relevant information. However, the low precision at 3.7% and IOU of 3.7% suggests significant inclusion of irrelevant text actually within the chunks. Our precision omega value of 16.74 indicates that even under optimal retrieval conditions, our chunking strategy includes substantial extraneous content. So when compared with the benchmark chunkers above, all the way up here, that recall performance aligns with state-of-the-art approaches at around 83 to 91%. Our precision metrics suggest opportunities for improvement through reducing our chunk sizes or refined boundary determinations. But honestly, not the worst for a very naive, simple approach of just grabbing 10 sentences and running that through left to right across our document. As you saw, however, we can pass in both a chunking strategy, but also a embedding function. So that means that we can actually evaluate not just the chunking strategy, but different embedders. So I ran a quick experiment with not OpenAI's embedding function, but actually with the sentence transformers All-Many LM-L6 V2 model here. And what we saw were these metrics. So our lightweight open source model actually decreased the performance pretty much across the board in comparison to OpenAI's state-of-the-art model, which is relatively to be expected, but now explicitly proven. And a little side thing about embedding functions, similar to how we had our custom chunking function that we're running evals on, you could also, in theory, create a custom embedding function. So they have a very similar setup from ChromaDB for just having a function where when you call it, we'll take in the documents and return embeddings. But now that we know how to run one experiment, what is a little bit more useful? Running multiple evaluations. Essentially, what we're going to be doing is running what's called a hyperparameter sweep, or multiple different variations of different hyperparameters, or changing the arguments across a chunker, and running these experiments to figure out which one might be the best combination. This is where we can start to really see the power and usefulness of something like this, because what we can do is actually define multiple chunkers and multiple embedding models and then test out every single combination of the two to see what might be the optimal system. As a note here, you don't necessarily just have to do one single chunking strategy. So while I did just include the sentence chunker with 5, 10, 15, and 20 sentences per chunk, you could also include something like a recursive token chunker, semantic chunker, all within all of these chunkers, along with many different embedding functions, and test all of the combinations across all of them. This is essentially how Chroma actually ran their chunking experiments across multiple different chunk sizes and overlaps here, but I'm taking this one step further by not just doing different setups of chunking strategies, but also across embedding models too. So down here, we're going to instantiate our general evaluation, and then just run through every combination of chunker and embedding model, which in this case of 2 embedding models and 4 chunking setups is going to give us 8 total experiments, and then return it all into a single data frame. So after running that, we can see the intersection over union, the recall, the precision omega, and the final metric, the precision, across every single combination of chunker, chunk size, and embedding function. It's a little easier to interpret these if we graph them out, so that's what I've done with all 4 of the metrics across all of the chunk sizes, as well as the embedding models. Blowing that up a little bit so that we can actually see it, we can see some interesting results. Obviously, our first immediate impact is that the OpenAI embedding function is giving us, in general, higher scores across the board. So we know that the OpenAI text embedding 3 large model, in this case, when compared to the All-Mini LML6 v2, is usually always going to be the better choice. One of the interesting things to note here is that we can actually see an increase in the recall performance going from 5 to 10 chunks with the All-Mini LML6 v2 model here, which it then subsequently falls off. So we do know here that if we were going to be using the sentence transformers model with this specific chunker, we would want to do 10 sentences per chunk to improve our recall a little bit. But we can also see that our precision tends to diminish as our chunk sizes grow bigger, and this makes intuitive sense because as we include more information, we're more likely to include irrelevant information across the board when they are recalled. While we are recalling the right stuff, we're precisely recalling maybe a little bit too much as these chunk sizes grow larger and larger. This is backed up by our theoretical perfect precision, which what we can see is that as we actually decrease the size of the sentences included in each chunk, it gets a little bit higher in theoretical perfect precision. And then finally, our intersection over union, that's going to show us the balance between recall and precision at the same time, shows this general downward trend that's likely being brought down by the precision specifically, but we can see that it actually tracks very well across both of the models and with relatively minor changes between them, except at lower chunk sizes, where OpenAI's embedding model actually tends to perform a little bit more. So now, armed with all of this data and nice looking graphs, we can make some decisions about what our chunking strategy should be and what embedding model we should likely be using. Of course, this isn't going to show us things like the actual subjective use of your pipeline and how relevant the end users are thinking the retrieved information and generated responses are, but it is a way to more explicitly measure our chunking and embedding models. So while these general evals are great, what's better than general domain specific? And lucky for us, along with the repo that Chroma put together, they also show their synthetic evaluation pipeline, which is how they actually created the original stuff here in the first place. At a high level, what this allows us to do is take in our document or set of documents, randomly select 4,000 character segments from them, and then use a language model, in their case GPT-4 Turbo, to generate natural questions based on this content, along with the relevant supporting references. We're then going to identify and extract the precise text spans that contain the information needed to answer the questions, and then run a couple filtering steps for duplicates and similarity to remove redundant or unrelated questions. So this will allow us to create the different questions and references that we were just running on the general evaluation, but specifically for any given document that we want to input. So this allows us to use their synthetic evaluation class here, and all we need to do is put in the corpora paths, which we're going to be putting in our 10K data here from NVIDIA, as well as an output CSV path, and of course an API key for OpenAI if using GPT-4. Their method, generate queries and excerpts, then takes in 3 specific keyword arguments, They have both approximate excerpts, which means that it's either Boolean true or false as to whether to use exact or approximate matching. Exact matching in this case will find the precise text bands in the source document, whereas approximate matching will pre-chunk the text into 100-character segments and allow references to span multiple chunks. Most of the time, you'll likely want to use approximate matching, as a lot of these semantic retrievals and language model generation context stuff can be a little bit fuzzy, and you don't necessarily need the exacts. It then has the number of rounds, which is how many times per document to run the query generations, as well as the explicit queries per corpus, or how many queries to generate per round. So I ran this for 105 queries on our 10K data, and if we look at a couple of them here, we can see that we've got questions, we've got references, and the ID, which is specifically just going to path over to our text document here. But before it's ready for our evaluations, we of course have to go through those filtering steps. So we can do the filter poor excerpts method with a threshold, which essentially is going to filter out questions where any of the references aren't sufficiently similar enough to the question semantically. This is done by embedding the question in the references and then comparing both through our semantic similarity. And then under a certain threshold, which their default is 0.36, that whole question and reference line is removed. So running this across our original 105 removed 29 where they were considered to be poor excerpts. Additionally, we want to remove any duplicates, of course. So we'll first look at exact duplicates and then remove them, and then embed all of the other questions and create a similarity matrix that compares every single question to every single other one, which will then apply a greedy algorithm to remove similar questions by keeping the first question and then checking out the similarity between that and all others and removing any later questions that are too similar. So the threshold here is going to be 0.78 by default. Then it'll move next to the question and repeat. So I use a threshold of 0.7 and that removed an additional 10 queries. And so then finally, down from our 105, we have 66, which then look a little bit like this. And so now we have our wonderful data set that we are going to be running our evaluations on of specific questions that are explicitly related to our text that we're working with, as well as the ground truth references. Similarly then, what we can do is do our single evaluation of just a sentence chunker with 10 sentences and our default embedding function and get our results back for just one combination with the chunker and default embedding function, which gives us all of these metrics after running, and comparing them to our earlier results, we see lower recall, but actually, funnily enough, higher precision, precision omega, and IOU scores. So with this in mind and seeing that it's working, we can perform the same kind of sweep that we did earlier, but now instead of running it on the general eval set, we can run it explicitly on our synthetically generated domain-specific eval set. This is going to have pretty much exactly the same setup as we implemented earlier, instead just pointing towards these. We then see our nice full final results across all of the different combinations, and again, our graphs here. We're seeing a lot of the kind of same performance as we saw earlier. Some notable things of interest is that the OpenAI embedding model on recall stayed relatively flat across 5 to 15, with only a drop-off at 20 sentences, whereas there was a large drop-off for the Almany LML6 v2 model at 5 to 10, but funnily enough, a slight increase from 15 to 20. There appears to be, however, a bit of a wider gap between our precision and IOU between the two embedding models, which we saw it track a little bit closer with our general eval data. But once again, our chunk size is still being detrimental towards our precision, which is dragging down our IOU when comparing the essential combination between them. We're also seeing, just in general, a lower precision omega starting point. So our theoretical perfect precision with our chunk size is not doing too hot when we apply it more specifically to our NVIDIA data set. So maybe this chunker is not the best for this. But with that, we've effectively shown how to now not just do sweeps over general evals, but also generate specific evaluation sets for your own data and run these same evaluations. So now we can make even more informed decisions about what combination of chunking and embedding models we should actually be using for our specific RAG pipeline. So to sum up a little bit of the final thoughts across this notebook, Chroma really provided a wonderful framework and powerful toolset for evaluating and optimizing RAG systems through the analysis of chunking and embedding strategies. We've uncovered a few key insights across our experiments. That is the chunking strategy impact. We demonstrated how different chunking approaches can actually dramatically affect our retrieval performance. Saw that smaller chunks consistently showed higher precision, but at the cost of potentially fragmenting related content, while larger chunks actually achieve better recall, but with more noise. We're also able to show embedding model comparisons and showed the performance gap between our state-of-the-art models like OpenAI's and the lightweight sentence transformers versions. So we can actually now more explicitly quantify the trade-off between cost and speed and performance when choosing embedding models. We then demonstrated how you can adapt these for domain-specific evals. So our synthetic dataset generation pipeline revealed how our general purpose chunking strategies might actually need different adjustments for specific document types. So our financial document from NVIDIA's 10K showed different optimal chunking parameters compared to our general eval corpus, highlighting the importance of domain-specific fine-tuning. And of course, we see the fundamental tension between precision and recall, with IOU providing this balanced perspective as a good middleman metric. These metrics can really help us guide the practical decisions about chunk sizing and strategies based off of our specific use case requirements. On top of that, we can see that being able to explicitly measure, define, and test across RAG systems can help us actually show where different performance optimizations lie, both in general and for domain-specific applications. So implementing a system like this, considering the metrics and being able to actually test these things can help you both prove and debug your system or choose the most optimal setup for you. However, one of the things that this does not necessarily test is, of course, all of the good subjective level research that comes from things like testing with end users and the subjective opinions of the people who are actually using the end result of your RAG pipeline. So this is more geared towards measuring our system's efficiency rather than the other subjective metrics like actual usefulness. A combination of the two types of testing is always going to be a better approach than just strictly one or the other. So hopefully this gave you a great insight into how you can start explicitly testing different chunking strategies, embedding models, and domain-specific evaluations of both to optimize RAG pipelines. With all that being said, hope you learned something interesting today. If you liked the video, drop a like on the video. If you have any questions, leave them in the comments below. And if you want to support the channel and see more, consider subscribing. I'll have this notebook along with further resources linked in the description below. And with that, thank you and have a great day.